to another instance of our remote condensed matter seminar. It's my great pleasure to introduce Professor Jian Wang, who's a Changjian Distinguished Professor of Physics at the International Center of Quantum Materials at Peking University. So he received his PhD in condensed matter physics in 2007 from the Institute of Physics at the Chinese Academy of Sciences. He then followed it up by his postdoc and research associate at Penn State before he returned to China to become associate professor at Peking University. And then he was later on promoted full professor in 2017 when he was also selected as Changjiang Distinguished Professor by the Chinese Ministry of Education. So his current research focuses on quantum transport in low-dimensional superconductors and topological materials. And he has authored more than 100 papers, amongst them Sciences, Science Advances, Nature Physics, Nature Materials, Nature Nanotechnology, Nature Communications, and a lot. And with this, I'm very much looking forward to his talk today that is on anomalous metallic states and Ising superconductivity in 2D crystalline superconductors. Okay. So with this, I would like to hand over to Professor Wang.
Okay. It's my great pleasure to give a seminar here. I would like to thank Qihua Xiong for the invitation and thank Professor Bent Weber for hosting this seminar. Today, I would like to share our recent works on anomalous metallic states and Ising superconductivity in 2D crystalline superconductors. My name is Jian Wang, and I'm from Peking University. Oh, there are some pictures for Peking University. This is our campus, and this gate is the West Gate, and this building is our library. And this is a lake with the name of no name. Okay, I would like to introduce a little about our research group and laboratory. Actually, in our lab, we have a 16 Tesla transport measurement system, and the lowest transport measurement temperature is 50 millikelvin for this equipment. And we also combined AFM, atomic ferromagnetic, atomic force microscope, and the tip point contact and angle dependent measurement options, with this system in this system. And so this system, we can use this system to measure most quantum materials or nanoscale materials. And we also have a ultra low temperature measurement system for lighting. It's the lowest temperature is 10 millikelvin, and we also combined the point contact measurement equipment with this equipment. So in this system, we also have the capability of a vector magnet. That means you can get the ferromagnetic field in any directions. Okay, besides the transport measurement systems, we also have a ultra high vacuum molecule beam epitaxy combined with a low temperature scanning tunneling microscope system. By this system, we can go the high quality 2D superconductors, and we can in situ to study the physical properties by STM or scanning tunneling or STS, scanning tunneling spectroscopy. Okay, today my talk includes this is the outline for today's topic. Part one, I will introduce a little the background. In part two, this is a major part. I will talk about anomalous metallic states and Ising superconductivity in 2D crystalline superconductor. The last part is just a one-page contact. I would like to share my opinion for the future perspective for 2D superconductors. Okay, background. High crystalline 2D superconductors have become one of the most interesting and most interesting frontiers. And from the Professor Iwasa's review paper in this journal, and there are three most important topics in 2D superconductors. The first one is the quantum Griffith singularity. Actually, this topic is originally the work is from our group, and actually I think 3 years ago I gave a seminar in NTU, and I talk about this discovery. This time I just a very quick just introduce it very quickly. And a second one is a quantum metallic state. This topic is a major focus in my talk. And the third one is the superconducting state maintained in huge in-plane magnetic field. Actually, people also call it Ising superconductivity. Of course, yeah, Ising superconductivity is only one part of this concept. Okay, we know quantum phase transition is a very important direction in condensed matter physics and also material science. And yeah, for 2D superconductors, such quantum phase transitions can be called superconductor-insulator transition or superconductor-metal transition. Yeah, SIT or SMT. Actually, such research can started in 1989. Yeah, yeah. At that time, people can grow amorphous superconducting fields. For example, amorphous bismuth field. Yeah, from actually it's Goldman's group. Yeah, this work from Goldman's group. Yeah, you can see when you change the thickness of the superconducting field, the superconducting film can show the superconducting state and the insulating state when you decreasing the film thickness. And at the middle point, yeah, at this point, the resistance almost constant, yeah, and this point is corresponding to the quantum phase transition point or quantum criticality. Normally, this resistance is a quantum resistance, and also you can change the electric field by applying gating, yeah, doing gating measurements for the superconducting field. You can also see such a superconductor to insulator transition. And also you can apply a magnetic field to see a similar transition. But this transition is called superconductor to metal transition because this resistance is not so high. It's not higher than quantum resistance. And so for the early studies, they got the Buckley Prize in condensed matter physics because the superconductor or supermetal transition is a quantum phase transition at 0 temperature, and this study is a very good paradigm for studying quantum phase transition. And you can see that in previous studies, people found at different temperatures, if you measure the resistance versus the magnetic field behaviors for the superconductor, you can see all curves cross one point, yeah, at different temperatures. Normally, we know the superconductor at lower temperature, you got the higher HC, but here for 2D superconductors, it's different. You can see all curves cross one point. This point is the quantum phase transition point. However, for our studies on crystalline gallium thin films grown by MBE system, we found we measured the resistance versus magnetic field at different temperatures in ultra low temperature region, and we found actually the curves across a region, not a point. Then we calculate the dynamic exponent, and we found that this exponent actually diverges when the field close to the critical field, or when the temperature close to the zero temperature. So our previous studies show it should be a constant, but we observed such a diverse behavior. So we noticed 40 years ago, yeah, Professor Graves predicted that if disorder can play a great role on the phase transition, then such a dynamic critical exponent can diverge. So in our quantum system, 2D superconductors, we observed such behavior. So we call it a quantum Griffith singularity. Yeah. So it's kind of a new quantum phase transition behavior. Yeah. Okay. Okay. So after our publication, Science also published a perspective paper to comment our result, and in this paper, they stressed, the author stated maybe quantum Griffith singularity is a potential universal behavior for superconductor metal transition in 2D superconductors. Okay, now let's focus on our today's major topic, quantum metallic state in 2D superconductor. Theorists would like to use anomalous metallic state, this term, but some experimentalists would like to use quantum metallic state. In my talk, I will use both terms, to describe same thing. Okay, we know very famous Anderson localization. You can see that in, for example, in a 2D system, a carrier, they can a carrier can or quasi-particle can move, move in opposite interfering trajectories. For example, clockwise and anti-clockwise. And actually, this behavior results constructive interference of a backscattering. That means the quasi-particle would like to stay here and doesn't like to move. So that's kind of a localization mechanism. According to Anderson localization, normally metallic state cannot exist in 2D system at absolute zero temperature. Yeah, that's a very famous work. And for the 2D superconducting systems, bosons are thought to exist in 1 or 2 ground states. Ground state, that means at absolute zero temperature, the state should be, So that so we call it a ground state. And for the bosons in 2D, bosons would like to condense in a superconductor or localized in an insulator. So here is the phase diagram, quantum phase diagram. Yeah, you can see that the y-axis is temperature, the x-axis is tuning parameter. For example, doping, disorder, magnetic field. You can see with an increase in disorder, for example, at zero temperature, for a 2D superconductor, it forms a superfluid or superconducting state. From this state to an insulator state or insulating state. And at this point, it's a quantum phase transition point. So these are 2 states, superconductor and the insulator. There are 2 ground states for 2D superconductors. And also we can understand this scenario by quantum mechanics. Yeah, according to quantum mechanics, if it's an ideal 2D system, 2D superconducting system, you can see in the insulator state, Cooper pair number fluctuations C. That means at every point, the Cooper pair number is the same, and leading to infinite uncertainty in the phase. Yeah, that's uncertainty principle. Yeah, and that means they are not coherent. So actually, although there are Cooper pairs in a 2D superconductor, but they are not superconducting. The system is insulating. Okay, in the superconducting state, In contrast, phase coherence obtains in a superconductor, leading to infinite uncertainty in the Cooper pair particle number. That means at every site of the system, although the number of Cooper pairs is uncertain, but they are coherent. So the system can show superconducting behavior. Okay, so bosons are thought to exist one of two ground states, condensed in superconductor or localized in an insulator. However, some experiments on thin metal alloy films have revealed that a metallic phase disrupts the direct transition between the superconductor and the insulator at zero temperature or closing to zero temperature. You know, in experiments, you never reach zero temperature, but you can lower the temperature very close to the zero temperature. Okay, here are some previous studies in 2D anomalous superconductors. The signatures of a metallic state were observed. You can see this work. For these curves, actually, they show the zero resistance at low temperatures. So you cannot see any data by such a log scale. And for these curves, actually, they show the insulating behavior at low temperatures. Yeah. But between these curves, there are some curves you can see. They show the resistance saturation at low temperatures. Yeah. They don't show zero resistance. Also, they don't show the insulating state, but they show some saturation states. This saturation states, resistance saturation states, are reminiscent of metallic behavior. Yeah, for example, for metal or for conductor at low temperatures, you know, the actually resistance saturates. That means the resistance almost doesn't change with the temperature changing or temperature variation. Okay, so this behavior is very strange because according to the theories, the bosons in 2D superconductors should be in two ground states, superconducting states or insulating states. But why? In some samples, you can see some such intermediate states, and also different groups reported similar behaviors. Yeah, they see some resistance saturation at low temperatures. Okay. Also in 2017, people studied amorphous indium oxide fields or found another signature of such intermediate metallic state. You can see they observed the resistivity saturation at low temperatures at some magnetic fields. And in these states, they call it intermediate metallic state or field superconductivity state. They found although resistivity shows some residual resistance, for example, from figure C, you can see that it's not a zero resistance at low temperatures; it's a residual resistance. But the Hall resistance or Hall resistivity shows almost zero. That means a particle symmetry observed in such states. Particle symmetry reveals field superconductivity in metallic phase of a 2D amorphous superconducting fields. Yeah. Okay. So last year, Professor Kaptunik, K. Wilson, Spivak, they wrote a review paper in Review of Modern Physics for the anomalous metallic state in 2D superconductors. And in this review paper, so here they show a phase diagram. You can see that the y-axis is temperature and the x-axis is the magnetic field. You can see the 2D superconductor can change from superconductor state at almost zero temperature to an anomalous metal state. And at this point, they call it a quantum phase point. It's a superconductor to semi-metal transition point. Okay, okay. They concluded, according to our previous studies, the characteristic of anomalous metal state in 2D superconductors that show two typical behaviors. One is resistance firstly drops and then saturates at low temperatures. Second, the sample should show giant magnetoresistance. The third, the sample should show a suppressed Hall response. That means particle symmetry. Okay, they also pointed out there's actually no satisfactory theory of anomalous metals. So this they hope in future people can get the satisfactory theory for such a behavior or such property. Okay. How about crystalline 2D superconducting system? We know our previous studies focused on amorphous 2D superconducting system, but with development of sample growth method, for example, MB, molecular beam epitaxy technique, or other extrapolation technique, or TMD materials like that. So people can study 2D superconductivity in crystalline 2D superconducting system. How about is that possible to observe the quantum metallic state in such a system? Actually, pioneering work is from Ivasa's group. They use the liquid gating, yeah, in zirconium nitride chloride. They by liquid gating, they observed the 2D superconducting behavior. And when they applied the perpendicular magnetic field, they found some resistance saturation at low temperatures. Yeah, you can see these behaviors. So their work published in 2015. And soon after their work, actually another group from United States, they observed similar behavior, yeah, in ultrathin niobium diselenide films. You can see applied magnetic field, the films show some resistance saturation at a low temperature, low temperatures. It sounds like quantum metallic state can be observed in 2D crystalline superconducting systems. However, almost the same authors from this work recently reported such quantum metallic behavior is from a high frequency noise. That means all these observations are not real, not intrinsic. They are from external noise, high frequency noise. Yeah, you can see that. I'll introduce it later. And so when they used the filter, the quantum metallic state became superconducting. So if existence of quantum metallic state in 2D crystalline superconductors are still under debate and challenge. Yeah, this is their work, yeah, published in Science Advances. And they found you can see their curve, their measurement curves. For left figure, it's a amorphous film, thin film. It's a very famous indium oxide thin films, superconducting thin films. You can see the red curves. They measure the red curves without filters. These curves these curves are resistance versus temperature at different magnetic fields. And they show some resistance saturation at ultra low temperatures. And looks like a quantum metallic state. But when they use filter, high quality filters, you can see these blue curves. And the samples show the zero resistance again. So these behaviors are not from an intrinsic property of the 2D fields. They are just from a high frequency. Okay. And they also studied the crystalline niobium diselenide flakes. And they also observed similar behaviors. You can see that. For the red curves are unfiltered curves. You can see beautiful curves for quantum metallic state, resistance saturation at ultra low temperatures. Please notice that the temperature they use 1/T as the axis. So the right part is the low temperature part. Okay, you can see the resistance saturation. But when they use high quality filters, they found the resistance becomes 0. Yeah, so it's just a superconducting state, not quantum metallic state. So the existence of quantum metallic state is under debate. Okay. So does a metallic ground state exist in 2D superconductors? With here, let me introduce our 2 recent progresses. First is anomalous metallic state found in nano-patterned high TC superconducting films. The second one is anomalous metallic state found in a type 2 Ising superconductor crystalline thin films grown by MBE. Okay, for first work, quantum metallic state in nano-patterned high TC YBCO films. You know, YBCO is a high TC superconductor. Yeah, we studied the YBCO films, and actually we use AL mask. Then by etching process, we can get the YBCO films with some holes. Yeah, you can see that here is the YBCO film, and this film there are many holes in this film. And with increasing the etching time, actually around the hole, the sample doesn't show superconducting. And with the increasing etching time, you can see the superconducting film can change from a superconducting state to an insulating state. So increasing etching time means increasing disorder in such high TC films. Okay, but between the insulating curves or insulating samples and the superconducting samples, there are some intermediate states. And you can see that in these states, even at ultra low temperatures, sample just show some metallic behavior. I will introduce this part behavior later. Okay, for our system, whatever the films show superconducting state or insulating state, the onset TC almost the same. That means the onset TC is around the 85 Kelvin, and only onset TC varies only within 15%. And so whatever the states or ground states, actually the onset TC for such films are almost the same. And here, let me introduce our evidences for quantum metallic state in 2D high TC films. Firstly, we use an ultra low temperature measurement system to measure the resistance saturation for high TC films. That's a trick, yeah. If you want to study the ground state, you can choose a high TC superconductors because their TC is very high. And then you use an ultra low temperature measurement system, you can get the more information for the ground state. Yeah. So in our measurements, you can see that the resistance saturation region is very huge, actually 10 or 100 times larger than previous studies because we use high TC films, and also use ultra low temperature to measure it. Our measurement can down to ultra low temperatures. And the second evidence is here. We also use high quality filters. For example, we use RC filter combined with some super filter. And you can see by using filters, we still see such a resistance saturation behavior at low temperatures. Not like that work reported. Yeah, in that work, yeah, if you use filters, such behavior becomes zero resistance. But in our situation, even you use a high quality filters, you can still see very good resistance saturation behavior at ultra low temperatures. And we also observed linear VI curves. That means, in such a metallic state. That means, it's very like traditional metal behavior. Yeah, it's a ohmic behavior. Okay, we also measured Hall resistance for the quantum metallic state. We found that although resistance, longitudinal resistance shows a resistance saturation at ultra low temperatures, but the Hall resistance shows almost zero. So that shows a particle symmetry for the quantum metallic state. And we also detected a huge or large magneto-resistance behavior for the quantum metallic state. So we got almost all evidence for the quantum metallic state. And this evidence have been predicted by some theories, or even some of them, even previous theory didn't predict. Okay. And not only in a quantum metallic state, actually in superconducting state and in insulating state, such insulating state, you can also get some resistance. Then you measure the Hall resistance. You found similar particle symmetry. Yeah. And because our field is a whole array, yeah, it's not why we fabricated holes in such a field, because we want to measure the quantum oscillations. Quantum oscillations with a magnetic field period of around 2K ost observed in superconducting state. You can see this, yeah, at different temperatures, you can see some quantum oscillations because there are many holes in superconducting field. Of course, these observations is in transition region, yeah, because at completely superconducting state, the resistance is zero. You cannot observe the quantum oscillations. But at in the transition region from superconducting to normal state transition region, you can measure resistance. You can detect such quantum oscillations for superconducting fields. And this period is consistent with one superconducting flux quantum. That means H/2E. If the quantum oscillations from quasi-particles, from electrons or holes, the period should be consistent H/E. But our observations shows the period of quantum oscillations consistent with H/2E. That means the Cooper pairs mainly contribute to such quantum oscillation. Okay. Okay, we also studied such quantum oscillations in quantum metallic state. You can see that. Very beautiful quantum oscillations for quantum metallic state. That means even for quantum metallic state, the resistance saturation state at ultra low temperatures, you can also Cooper pairs dominate the transport behavior, because such quantum oscillations are from Cooper pairs, not from electrons or holes. Yeah. And also, even in insulating state, if you can still see some resistance, you can detect the quantum oscillations. Such quantum oscillations also show H/2E behavior. That means even in super insulating state, actually Cooper pairs dominate the behavior. Yeah. So here we studied the quantum oscillations amplitude with at different with decreasing temperatures, and for superconducting state, insulating state, and anomalous metallic state, or quantum metal metallic state. You can see that for the superconducting state, with a decrease in temperature, actually the amplitude of quantum oscillation is increasing very quickly. It's increasing very quickly. Of course, at ultra low temperature, because the sample shows a zero resistance, you cannot get the information. But the trend is the amplitude increasing very quickly. It's easily understanding because with the decrease in temperature, the coherent behavior is very becomes more and more robust. So the quantum oscillations should be very robust. And for the insulating state, actually at low temperatures or ultra low temperatures with decreasing temperature, the amplitude of quantum oscillations decreasing. Yeah, it's also easy to understand because when the Cooper pair is localized, and if a Cooper pair is completely localized, no carriers in the system, so no quantum oscillations can be observed. And so with the decrease in temperature, this kind of quantum oscillations become weaker and weaker. But for the quantum metallic state or anomalous metallic state, actually such a quantum oscillation amplitude saturates at ultra low temperatures. That means in such state, actually phase coherence it's a fixed. Phase coherence is fixed. It's not diverse, not localized, but like a constant or like a saturated value. For example, in figure E, actually we compared our work for we used the formula in quasi-particle interference, for example, AB effect. We use such a formula, and if we compare, if we consider our Cooper pairs, because in high TC superconductors, the Cooper pairs, the coherence, actually the Cooper pair coherence length is less than 1 nanometer. So if we compare one Cooper pair as a quasi-particle, their phase coherence length can be calculated by quasi-particle quantum formula, interference formula, and we found, indeed, for quantum metallic state, such a phase coherence length saturates at ultra low temperatures. But for the insulating state, actually it's a decrease. The phase coherence length decrease. And of course for superconducting system state, it should be diversing or like that. Okay. So the saturation of a phase coherence, plays a prominent role in the formation of this anomalous metallic state. That's our conclusion. Okay, here's a phase diagram for our studies. For our YBCO films modulated by hexagonal array of holes. You can see that at ultra low temperatures, the sample show change from a superconducting state to a quantum metallic state, then across a point to a Cooper pair insulator state. That's the phase diagram. But whatever the sample in superconductor or quantum metal or insulator ground state, Cooper pair dominate the behaviors. That's our summary for this work. Okay, so we found the disorder-induced superconductor anomalous metal insulator transition in high TC superconducting films, and we found the very strong evidence for the quantum metallic state, and we also observed the quantum oscillations even in quantum metallic state. That can show the Cooper pairs dominate the behavior. So it's a very important information, and also our analysis shows that the saturation of a phase coherence could be the origin of anomalous metallic state into the system. Okay, so when we put our work in archives, Professor K. Wilson wrote commentary article in Journal Club for condensed matter physics, and with the title Evidence of Anomalous Metallic Phase in High Temperature Superconducting Device. And they conclude the 3 advantages in our work. One is we use ultra low temperature to study our measurement down to ultra low temperatures for such high TC superconductor. So for the anomalous metallic region, our region is 10 to 100 times higher than previous studies. And the second one is we can observe the quantum oscillations with the period show Cooper pairs dominate the transport behaviors in metallic state and even insulating state. And the Hall resistivity also show very small value in measurably small value. And so he concluded in this article, and our work may help to add our understanding on quantum materials. Okay, like that. Okay, so also in Science, Science also published a perspective paper for our work with the title "Free at Last: Both Metal Uncaged." So teasing is over in this paper. Yeah, in this paper, Professor Phillips mentioned teasing is over. Bosons can exist as a metal. Okay. I would like to acknowledge my collaborators in this work. The student Yang Chao, actually his student of Professor Yan Li, and also Professor Jie Xun. In the beginning, Jie Xun contacted me for such for this collaboration, and after 2 years study, we found that we should focus on the quantum metallic behavior in this system, and my postdoc Yi Liu, and he's in charge of transport measurements on the most important behaviors in this system, and Professor James Wallace. Yeah, James actually the sample fabrication fabrication method is originally from Professor James Wallace group, and other collaborators. Okay, second one, anomalous metallic state in type 2 Ising superconductor palladium diterite crystalline ultrathin films grown by MBE. Yeah, I found my time is a little yeah, my time is okay. Yeah, or I should finish soon.
Yeah, we're slowly running out of time. I think it's scheduled until 11:30, so maybe 10 minutes, and then we can have a very brief question and answer session. Okay. In 10 minutes, I'll finish my talk. Yeah, this time maybe I don't need to introduce Ising superconductivity. Yeah, I just focus on anomalous metallic state. Okay. Oh yeah, this part is very short. Yeah. And in this, we know in 2019, one paper tested whatever amorphous thin film superconductor or crystalline 2D superconductor. When most previous studies, they don't use high quality, they didn't use high quality filters to measure their samples in ultra low temperature region. So maybe their behaviors, their observations are just external noise. Yeah, their behaviors might be from the external high frequency noise, because they show when they use high quality filters, the samples show superconducting ground state, not a quantum metallic ground state. So for high quality crystalline 2D superconducting system, is it possible to get the real evidence for quantum metallic state, and also quantum metallic state at that time hadn't been reported in high quality 2D superconductors grown by MBE. You know, MBE can grow very high quality 2D superconductors, but
until 2019, no MBE grown films show such quantum metallic behaviors. So it's very important to observe quantum metallic states in high quality MBE grown crystalline thin films with high quality filters. So we studied palladium diteride film down to 15 millikelvin by our film is the thinnest film is 4 monolayer thickness. Okay, so actually by in our measurements you can see that at very low temperatures, at ultra low temperatures, actually samples in some perpendicular metallic fields, the samples show resistance saturation behavior. And in all our measurements, we use very high quality filters, at least as good as the previous in previous reports, or even better than previous reports. We use very high quality filters, and so all these observations actually can we can exclude the possibility of external high frequency noise. Okay, but okay, so that's a very strong evidence for a quantum metallic state in MB grown high quality 2D superconductors. And of course, we also observe such linear VI curves in our quantum metallic state. And we also did some fittings. Yeah, we use a quantum creep model, or you can also call it quantum tunneling of a vortex model. Yeah, you can see such model can fit our data very well. Okay, summary for this work. It's the first time to observe the quantum metallic state in MB grown superconducting crystalline films. And we offer the strong evidence of a quantum metallic state in 2D single crystalline superconductor conducting films by using high quality filters. Second is actually this film is very impressive. By MB, you can get the microscopic high quality films. Of course, the thickness is very thin. It's around 1 nanometer or like that. Yeah. But the error can be very huge. And normally for such thin and huge superconducting films, you need a protection layer to protect. Otherwise, it's very easy for the sample to lose the superconductivity. However, for our palladium diteride films, we found that the films is ambient stable. Yeah. Shows ambient stable superconductivity. That means you don't need a protection layer. And for our in our experiments, even after 2 years, you don't need after 2 years, the sample can still show very good superconducting behavior. So it's a very impressive 2D superconducting system. Okay, that's maybe good for material science. Okay, after our publication, yeah, the science science editor's choice selected our paper in science, and with the title of an unusual superconductor. Yeah. Okay, I would acknowledge my collaborators in this work. Yeah, my postdoc Yiliu, yeah, he's in charge of the transport measurement, and Professor Xilin, and his student Jian Sun, and also our collaborators in Tsinghua University, Professor Li Wang. Yeah, he's in charge of the sample growth with his student Chong Liu, and also our theoretical collaborator Yong Xu. He did some calculation for type 2 Ising superconductivity. Actually, today I may not have time to introduce the type 2 Ising superconductivity. Actually, this term was suggested in a discussion meeting between me and Yong Xu and other collaborators. And I would like also I would like to thank our thank the other collaborators. Yeah. Okay, the part 2 is Ising superconductivity in 2D crystalline superconductors. But today I don't think I have time to introduce this, so I'll skip it. It's a kind of a behavior the spin polarized perpendicular to the film. So in-plane magnetic field cannot destroy the superconductivity. Okay, okay, I'll skip this and to the conclusion part. Part 3, yeah, future perspective in 2D superconductors. Okay, so quantum metallic state as a ground state is a very debated and focused issue. So we got some evidences for such a ground state, and but this the studies in on this topic is still not is still actually new. We don't know too much about such we don't know too much about such a state, because even today, yeah, more and more people can accept the existence of a quantum metallic state, but there's still a debate, but still we don't have a very satisfactory theory for such state. So we need more techniques to study such a quantum metallic state to see more properties of such state. And we need more experimental techniques, and the microscopic theory is called for quantum metallic state. And for the quantum Griffith singularity, that means a new quantum phase transition in superconductors, we still need more experimental techniques to give more information. And for Ising superconducting system, actually actually the most important fix in future, maybe people can combine topological superconductivity. Yeah, maybe people can detect topological superconductivity in Ising superconducting system. And in many systems, actually, many 2D superconducting system, we can use the interface to induce superconductivity or enhance superconductivity or change superconductivity. So it's a very powerful tool, and in future, maybe especially for TMD studies and graphene studies, you know, the twisted graphene actually is also kind of an interface effect. Yeah, maybe you can get more more results in this topic. And also 2D superconductor is a very good plateau to study 2D high TC superconductivity. Maybe can give some new information for the high TC superconductor committee. And the last but not the least is the Majorana in 2D superconductors. Actually, our group found some in 2D high TC superconductors. We found some evidence of Majorana. So in future, maybe this is a new topic. Okay. Okay. Thank you for your attention.
Yes, thank you, Professor Wang, for a very, very interesting talk. I suggest we open this session to questions. Okay, maybe I'll start. So you mentioned that oftentimes a saturation in the normal state resistance, as well as a saturation in the phase coherence length is taken as a sign of high frequency noise. Could you give us an indication based on the dephasing time, what you estimate for the frequency range, and can you give us some details of the filtering that you use?
Okay, very good question, and a very deep question. Yeah, so let's see if I have some information or not for that. At least I think the frequency, I think we have some information. Yeah, here we use the filters. We believe actually as which frequency high frequency noise can affect such a such a fragile superconductivity in 2D superconductors. Now we believe this actually is I think it's a amhertz. That means a million hertz. Yeah. In such frequencies, such frequency can easily change the superconducting state to a residue resistant state. Of course, for other regions, actually, we can screen more, much more. Normally for such a frequency and even higher, actually, I remember it's 1% meaning for the 1%. 1/, meaning percent of energy, noise energy can affect our measurement. Others we have been filtered. Yeah, that's for the frequency information. And for the coherence time, it's very good question. Yeah, let me see if I calculate it. I'm not sure. Of course, we have such lengths. Maybe we have some information, but I cannot remember the value. But the such a length value is around 100 nanometers. Yeah, that's for such a phase coherence length value. For the time, I cannot remember it exactly for the tau. Yeah. And I think that so it's this mechanism is very new in it's we first tested this mechanism because we are the first group to observe the quantum oscillations in a quantum metallic state, so we can get such information, and this is very important. But also of course also high quality filters are very important too, because such a decoherence, if it's from the intrinsic behavior, it's very important. But if it's just from external noise, it's not so important. Yeah. So we cannot call it call the quantum metallic state or ground state if such behavior is from external noise. So I think combine this information, we can see our evidence for the anomalous metallic state is strong. Okay, I hope I answered some of your concerns or comments. Yeah.
Thank you. Ranjan.
Yes. Jian Wang, excellent talk, and we were very inspired by your bosonic metallic state science paper, and now we are trying to sort of observe this metallic state at terahertz frequency, so that we will be able to tune it with light and study the ultrafast dynamics of such a state.
Oh, very good topic. Yeah.
Yeah. So one issue that we've been facing. So we have quite a good experience with nanostructuring of large area superconducting nano domain metamaterial devices, and that's why we want to try this out. But we've never worked with films with thicknesses lower than 25 nanometer. So my question is that, how did you guys get such good 12 nanometer YBCO films?
Actually we use magnetic sputtering to grow such high quality films. And actually, it's Professor Xun Jie and Professor Professor Jie Xiong and Professor Yan Rongli. Yeah, they grow such film, and they have many years experience in grow high quality YBCO films or high TC films. So yeah, so if you need some further details, maybe you can write me or write them for the more information. Okay.
Sure. And is this state also thickness dependent? And your somehow when you vary the etching time, do you use many samples or you just vary the etching time of the same sample?
Oh, very good question. Yeah, we use different samples. So we need much time to measure to carry out our measurements, because every curve here, I think it's a 17. 17 curves here. Every curve from different samples. So we measured different samples for different etching times.
Sure. Thank you. And does it have any thickness dependent? I mean, this whole effect?
What do you mean? Yeah,
film thickness dependence.
Oh, film thickness dependence. It's a very good question. By the way, we didn't carry out such measurements because only for such measurements we spent a lot of time. Maybe in future we can control the thickness to see what will happen. Yeah, very good question.
Okay. Okay. Thank you.
Thank you.
Yes, thank you, Ranjan. Do we have any other questions in the audience?
Hey, Jian, I have a question here. I think it's related to the Ranjan's question here. Since we're already in the slide. Now, you increase the disorder. I assume that mainly because of the etching of the plasma, right? Now, when you do the etching, you introduce disorder, but at the same time, I think you also affect your carrier density. Is that true?
Yeah, it's a complicated process. Yeah, I can try to answer this question. Also Professor Singh's question. Yeah, it's when you're increasing, for example, from figure C, we can see that when you're increasing the etching time, although this hole doesn't change, but around this hole, yeah, the sample degrading, yeah, the material degrading. And more material cannot be superconducting due to the disorder or like that. Maybe the carrier also because then only this small region YBCO can be superconducting. So like a Josephson junctions. And also I think carrier density also be affected. Actually, besides that, also the effective thickness also be affected. For example, although the thickness of YBCO film is 12 nanometer, but I asked the students to calculate the effective thickness. That means if this part is not superconducting, it's hard to say. We just calculate if without such a holes. If you remove the whole region, and calculate the effective thickness of the film, then the effective thickness can be comparable to 1 nanometer. That's why you can still see 2D superconducting behavior in such 12 nanometer thick films. So this process is because 1 nanometer you can compare the coherence length of Cooper pairs with the thickness, but 12 nanometer maybe a little thicker, a little thicker. And of course, YBCO is a layered materials, it's a positive to be observed, but the thinner the better, you know that. Okay, very good question.
Okay, maybe I've got one more. Towards the end of your talk, you briefly touched on the transition metal dichalcogenides. Now, many of them, including NBSE2, but also palladium ditelluride, I believe, are multiband superconductors. So how do you suspect the multiband nature would affect this anomalous metallic state?
Oh, you mean multiband nature in TMD 2D superconductors? If such multiband nature can affect metallic state?
Yeah,
that's your question.
I mean, you said there's no strong theory on this anomalous metallic state, but I mean, are there any ideas how multiband nature of superconductivity would affect the state?
Wow, it's a very very deep question. So even for such a state, even for such a state, you can say such a state. Even for such a state, there's no very good theory or microscopic theory to explain it. And actually, this state is we consider this state for 2D superconductors. For the initial point or for your starting point, you don't. I think in beginning we don't need to consider the details of the superconducting mechanism. If the 2D, it's a good 2D superconductor. 2D superconductivity can be observed. Then we can study to see if there's a intermediate ground state that's called anomalous metallic state. If you can see such a state, and that's a more general picture, for a picture for 2D superconductors or 2D boson system. But of course, when you deeply studied we also have some evidences for this, because we in YBCO fields you can see such behavior, similar resonance situation. But also we can see such in TMD 2D superconductors, as you mentioned, But the TMD 2D superconductors sometimes multi-band can do effect, but even you have multi-band effect or you don't have multi-band effect in your 2D superconductor, you can always see similar resonance saturation effect. So the quantum so metallic ground state is a more general picture for 2D superconductors. But of course, if you study it deeper, maybe such intermediate state or such a metallic state shows something different with other single band superconductors, then you can consider multi-band, how the multi-band can affect the quantum metallic state. That's very good temperature, but well, that's very good question. And I think our people or our experts in this field should, in future studies, maybe we can focus on this issue. Okay, thank you.
Thank you. Do we have any more questions? So if not, I think we're 10 minutes over. In that case, I believe we can conclude the session. So thank you, Professor Wang, once again for an excellent talk. This was very, very exciting. And it was a great pleasure to have you.
Thank you. Thank you very much.
And thank you so much for arranging this.
Thanks a lot. It's my great honor and a great pleasure.
Okay, and I believe we can conclude the meeting then.
Yeah. Okay, bye-bye.
Okay, bye.